Hypothalamus Artificial Intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its products and experiences in supply chain optimization. This video is confidential and may not circulate outside the receiving company without HI's authorization. Artificial hypothalamus. The power of today's technology is not in the mathematical calculations that it allows to perform, it is in the mathematical calculations that we can imagine that we can perform. Enterprise-wide optimization. A company's value chain is made up of two chains, which are strongly interrelated. Demand chain determines all the processes that are carried out to attract customers in the markets, and supply chain determines all the processes that are carried out to produce the products that customers want to consume. Jeremy Shapiro, professor of the Massachusetts Institute of Technology, says, "The primary benefit of a DSS is the explicit reduction in costs and the increase in profits. Cost reduction of 8% performed by our client is not atypical. In our experience, the integrated analysis of planning problems, using mathematical models, determines strategies between 3 and 20% cheaper." Many companies do not allow them to publish their positive experiences, as they consider that an advanced decision support system gives them a competitive advantage. The models developed by HI aim to support two activities within the industrial company: sales and operations planning, and integrated business planning. The optimization models for industrial value chains can be divided according to the productive chain they support, demand chain, and supply chain. This presentation focuses on supply chain. HI divides the conventional industrial sector into industrial and bio-industrial. This presentation focuses on industrial companies. Industrial activities optimization. The diagram presents a traditional supply chain-oriented decision support system. The coordination of activities is: demand characterization of clients and competence, resilient supply chain design, sales and operations planning, multi-echelon inventory optimization, global sourcing optimization, production scheduling, available to promise, scheduling of production to clients and client to routes, and distribution planning and scheduling. These activities cover the entire hierarchy of decision-making: strategic, tactical, and operational. The focus of coordination is on the correct linking of the models of demand planning and production planning, and on the representativeness of these two processes. These two models are considered essential for the optimal management of the value-added chain. The traditional approach to operations planning, SANDOP, is: develop a deterministic model of the productive infrastructure network, and chain it with parameters that represent the production environment, sales, maintenance, and finance. Due to the growth of computer technology, the state-of-the-art is to develop multiple functional models, which can be run independently, or which can be integrated into a monolithic model that is solved using the concept of autonomous, real-time distributed optimization. The table presents a summary of the models developed by HI. Supply chain design, resilient supply chain design, sales and operations planning, industrial production available to promise, industrial research and development, maintenance optimization, supply chain and financial modeling, industrial services optimization, inventories policy, global sourcing optimization, production scheduling, and industrial products available to promise. The artificial brain is the evolution of DSS under the Industry 4.0 revolution, that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. As part of its methodology, all the mathematical models developed by HI are related to an information system, unified through the data model, which facilitates communication between models. An example is this holistic view is: Oil enterprise-wide optimization integrates mathematical models for each of the links in the oil supply chain, in such a way to management the planning of the supply chain with a holistic vision. The design of High Oil AWO was the result of work done for a multi-business oil company. The union of models, and their coordination, forms the hypothalamus of an oil enterprise. The current computational power allows to model detail the supply chain, considering individually all the systems that compose it. This allows to visualize all the existing bottlenecks, and that affect the maximization of economic gains. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. In 2010, High executed the project The Hypothalamus of an Oil Organization. Challenge: design and implementation of a DSS decision support system. For the optimization of energy resource that links all stream of the supply chain petroleum products, with emphasis on the consumption and marketing of the energy used by the network. Solution: design and prototype implementation of the DSS that following models. Production of crude oil. Transportation of crude oil. Oil and biomass refining. Production and industrial services, and transport of refined products. Result: the model is the base to the formal implementation of the value chain model for a Latam petroleum company. The models were delivered in prototype version, in the sense that the oil company did not have the database in the expected time. This is one of the most important projects developed by High. Project: Bavaria Supply Chain Design. Challenge: in 1990, Bavaria hired High to implement tactical and strategic planning optimization models, using 386-486 Intel CPUs, because its actual models does not run properly in its IBM mainframes. Solution: the models were implemented using the first version of the Bender's multi-level partition and decomposition methodology, that is part of the High Optex Optimization Expert Robot. Result: Corporate Industrial Planning Decision Support System, PCSI, oriented to strategic and planning models. In 1998, PCSI made it possible to plan a beer supply chain of 18 production plants, 42 bottling lines, and more than 230 SKUs. The models have been used for over 25 years, primarily to support SandOp activities. Implemented in IBM OPL using IBM Plex. Project: Beer Supply Chain Optimization. Challenge: in 2014, SABMiller, Bavaria, hired High to upgrade tactical planning optimization models, according to the state-of-the-art of information technologies. Solution: design and implementation of new models, to support SandOp process that includes the modeling of detailed process in the breweries and work shifts in factories. The new model includes detailed modeling of the area of breweries, work shifts in factories, product substitution, the assembly of combos in distribution centers, and reverse logistics of the processing of bottles and baskets. Result: implementation of powered new mathematical models using IBM optimization technologies. Research and Development Project, Supply Chain Design and Financial Risk Management. Challenge: to implement an optimization model that integrate the production with the financial modeling to permit the enterprises to implement optimization models for the design of global supply chains. Solution: design and implementation of an optimization model that connect financial and fiscal activities, ALM, with design supply chain, SCD. Conventionally, the design considers that supply chains are designed to function optimally under normal conditions, without considering the resilience of the chain to extreme events, natural disasters, flow interruptions for abnormal reasons, strong changes in prices, availability of raw materials, etc., which represent a major risk factor that entails, among many, increase in operating costs, penalties or costs for not serving the market. Based on principles of stochastic and robust programming, the goal is to design a supply chain that operates very well under normal conditions, and well when extreme events occur. Result: implementation of SCD/ALM model applied to a real beverage supply chain in Peru. Consulting Project, Global Supply Chain Design. Challenge: in 2024, a multi-Latin company hired High to redesign its global supply chain, in order to determine how best to serve the Latin American and North American markets. Modeling involves the coordination of an international network of raw material plants and end product plants. Solution: applying the new high methodology for the resilient design of global supply chains, including financial risk management. The model is called GSCD. Result: project in progress. The result will be the implementation and use of the GSCD to determine the best global supply chain for the multi-Latin enterprise. The high methodology for mathematical modeling of the supply chain network design involves at least 3 types of models. Investment coordinates the logic of investments in the present and in the near future. Operations estimates operating costs and operating policies, which are derived from investments, and financial coordinates the cost of investments and operations with financial flows to ensure their viability and financial convenience. Additionally, it must control the financial risks due to investments. The first model will be called LogFin. It is oriented to define the investments to be made in infrastructure necessary for production. It corresponds to a dynamic model that defines, for each period of the planning horizon, the investments to be made, and the network for short-term operation. As input parameters, it should consider the costs of investment, rate of return on capital, the costs of loans, payment period, and other financial considerations. Model constraints are related to investment logistics and financial risks. The main results of the model are NPV, net present value, of the investments, VAR, value at risk, cash flow, and network design for the first periods. The second model will be called SANDOP. It is aimed at simulating industrial operations for each possible network proposed by the investment model, LogFin. As input parameters, it should consider, at least, the forecast of demand of final products, raw material supply, operational costs, and sell prices. The model can be extended to consider other aspects such as technological innovation that affects the productivity of processes, new technologies, which may affect market prices, and others that are considered convenient. In general, all input parameters are uncertain, and it is appropriate to consider that this makes a stochastic programming model based on scenarios. This characteristic makes the LogFin model a coordinator of the evaluation of the scenarios to be considered in SANDOP. It corresponds to a dynamic model that defines, for each period of the planning horizon, the industrial operations, and the storages of materials. In certain cases, it may not be necessary to consider product storage, because it may have little impact on investment costs, and additionally, it may be considered that its offer is always provided by the market with stable prices. This is not the case for oil storage, where the market prices and the supply of oil and gas is uncertain with high volatility. The constraints of the model are related to the industrial production process. Normally, there are several alternatives to simulate this process. At one extreme, we may formulate a very simple model, perhaps a few aggregate equations, that synthesize the process. At the other extreme, we may formulate a detailed model that simulates the processes with great certainty. The decision is of the modeler. What is true is that the available computer technology, computers plus solvers, allows very advanced models in this aspect. Therefore, the level of detail will grow exponentially in the next years. The main result of the model is the operational simulation for each period for each scenario. Data that are necessary to evaluate the future cost function that generate the decisions of the present. The third model will be called ALM. Its objective is to simulate the assets and liabilities management, ALM, considering the results provided by LogFin and SANDOP models. ALM is a modeling consolidated methodology that focuses on the financial modeling of companies. Its growth is generated at the end of the past century, in the financial sector, as a result of the Basel Accords. The minimum ALM modeling should be oriented to evaluate the NPV, for a pre-established ROI, return of investments. It will provide the financial statements, balance sheet of assets, liabilities and equity, income statement, profit and loss, after tax, royalties, and other contributions, and cash flow. Extended ALM modeling may include investments in alternative assets and liabilities, payment of dividends, capital repatriations, capital flow, and multiple currencies. In healthy logic, this model must be the coordinator of the holistic investment process, since it is the financial vice presidencies of the organizations responsible for endorsing investments in production assets. The results of the holistic optimization process are probability distribution functions for the primal variables and the dual variables of all DSS models. For example, the NPV. In simpler modeling, these distribution functions are obtained using spreadsheet simulation models. The results are not comparable because of the methodological difference in the approach. Consulting project, Global Supply Chain Design. Challenge: to implement the supply chain model for companies importing products to Colombia, from products produced in any country, to be used by a logistics operator. Solution: design and implementation of an optimization mathematical model, to determine the services and the facilities that optimize the global distribution network. The model includes the importation process, including Incoterms, and the distribution national process, allowing to decide to use infrastructure of the importer, and/or of the logistic operator and/or alternative third party. Result: a MIP model that evaluates the importation process for any multinational client of the logistic operator. It was used in consulting projects for logistics operator. Supply chain expansion and financial risk management model. Challenge: in 2008, Czech contracted HI to provide a model for optimizing the expansion of its electricity supply chain. Solution: implement a stochastic expansion model that includes financial risk management based on CAIR, conditional value at risk constraints. Result: a mathematical optimization model implemented in C using GNU solvers. Consulting project, Distribution Chain Design. Challenge: implement an optimization model to design the customer's distribution chain. Products: pharmaceuticals, personal care and household hygiene, processed foods, and agriculture and veterinary. Solution: design and implementation of an optimization mathematical model to determine the services and facilities that optimize the national distribution network. The model includes inverse logistics process. Result: a MIP model that designs the national supply chain and simulates the operations. Optionally, the model may use stochastic programming approach, based on probabilistic scenarios for the parameters like demand, prices, and others. Project, Decision Support System for the Optimization of a Pharmaceutical Supply Chain. Challenge: implement tactical planning and scheduling models, to optimize the pharmaceutical supply chain. Solution: implementation of a set of optimization models that integrate production planning and scheduling in plants, to minimize machine times and format changes, optimize inventory policies, minimize the cost of handling raw materials, and maximize the level of customer service. The model includes work shifts in factories. Result: a DSS that integrates the following models: medium/short-term demand forecast, SANDOP tactical planning, inventories policies, global sourcing optimization, and scheduling production lines. The DSS was integrated with SAP ERP. Project, Decision Support System for the Optimization of an Auto Part Supply Chain. Challenge: to implement a DSS that includes tactical planning and scheduling models to optimize auto part supply chain, mainly car seats. Solution: implementation of optimization models that integrate production planning and production scheduling at the production plants to minimize setup times and format changes in the machines, to optimize the inventory policies and raw material acquisition planning, and to maximize the service level. The simulation of the seat manufacturing process is detailed and includes substitute production formulas with different characteristics of the polymers, which impact the setting speed and temperature, which affects the service life of the molds. The mathematical model manages the service life and production of molds. Result: a DSS that integrates the following models: demand forecast medium/short term, SANDOP tactical planning, inventories policies, and scheduling production plants. Consulting project, Hospital and Surgical Equipment Supply Chain Optimization. Challenge: To solve the planning processes of hospital and surgical equipment and services in SLA, Spanish Latin America, Colombia, Mexico, Chile, Peru, Costa Rica, and Puerto Rico. Solution: design and implementation of a mathematical model for optimize the planning processes of hospital services of surgical equipment. It produces customer service policies and optimum inventory levels at each distribution center. Result: a consulting project, using the mathematical model, that proposed customer service policies that estimated a saving in CapEx for inventory of 35%, with respect to the policy plan before the study was carried out. Project: Dairy Supply Chain Optimization. Challenge: to implement tactical planning model, to optimize the supply chain, in the short-medium term, of a large dairy enterprise. Solution: implementation of an optimization model to support the SANDOP production activities, including the following type of products: beverages, milk, baby food, desserts, cheeses, cream and butter, and finesse products. The model includes work shifts in factories, and blending processes to prepare the base products. Result: an optimization model to support SANDOP production activities. Project: Ceramic Supply Chain Optimization. Challenge: to implement tactical planning model to optimize the supply chain in the short-medium term for ceramic industries. Solution: implementation of an optimization model to support the SANDOP production activities for sanitary ware. The model includes work shifts in the factories and a detailed simulation of the furnace. It also considers the process of selling and transporting products to different markets. Result: an optimization model to support SANDOP production activities including the start, stop of furnace. Proof of concept: beverage supply chain optimization. Challenge: to implement a tactical planning optimization model oriented to beverages industries, soft drinks, waters, juices, etc. Solution: design and implementation of a SANDOP optimization model for beverages industries. Result: use the mathematical model in a proof of concept for a large beverage company in Peru. Project: plastic supply chain optimization. Challenge: to implement tactical planning model to optimize to supply chain in the short-medium term for plastic health products. Solution: implementation of an optimization model to support the SANDOP production activities that includes the following type: syringes, probes, etc. The model includes the work shifts in factories. Result: an advanced planning and scheduling system, APS, to support SANDOP production activities. Project: available to promise optimization. Production, inventory, and distribution models. Challenge: to implement an informatic tool to allocation of products to client orders, and delivery orders to trucks. Solution: implementation of design and implement an ATP, available to promise, optimization model, that finds the optimal allocation of products to client orders, and delivery orders to trucks. Result: an optimization model to support ATP activities. The solution is linked to its ERP and WMS to execute the next 15 dispatch plan days. For the first few days the model make emphasis in the customer service criteria. For the medium term, 2 to 3 weeks, the operations cost is the priority. Research and development project: food supply chain optimization. Challenge: to implement a tactical planning optimization model oriented to food industries, pasta, jams, soups, etc. Solution: design and implementation of a SANDOP optimization model for food industries. Result: use the mathematical model in a proof of concept for a large food company in Peru. Research and development project: textile supply chain optimization. Challenge: to implement a tactical planning optimization model oriented to textiles industries. Solution: design and implementation of a SANDOP optimization model for textiles industries. Result: use the mathematical model in a proof of concept for a large textile company in Peru. Maintenance planning and scheduling of electricity assets model. Challenge: to develop a maintenance planning and scheduling optimization model. Solution: design and implementation of a maintenance of hydrogeneration electricity assets, to have a safe and reliable operation of the system, to improve relevant operational aspects such as functionality, safety, plant productivity and profitability of the operation. The model includes the electricity trading based on long-term contracts, and/or electricity spot market. Result: a mathematical optimization model implemented in C using GNU solvers. Multi-echelon dynamic inventory optimization model. Challenge: to implement a multi-echelon dynamic inventory optimization model for pharmaceutical distribution. Solution: implementation of an optimization model to generate integrated inventory policies that consider simultaneously multiple products, the distribution network, the consumer centers, sourcing offers, lead times, production and/or distribution, capacity constraints, and work capital constraints. The model is based on a stochastic programming model that can produce Pareto curves for the level of customer service, probability of stock out, versus inventory policy cost. Result: a multi-echelon dynamic inventory optimization model. Delivered to customer. Pharmaceutical industrial operations scheduling model. Challenge: to implement a scheduling pharmaceutical production plants optimization model. Solution: implementation of an optimization model to scheduling pharmaceutical production factories. The model includes, in detailed formulation, the manufacturing versions, and the lifetime of the raw materials. Result: a scheduling production optimization model. Two versions of the model were delivered, GAMS and C linked to Plex and Gurobi solvers. Global sourcing optimization model. Challenge: to implement a global sourcing optimization model for buy raw materials for pharmaceutical products. Solution: implementation of an optimization model for buy raw materials for commercial products, considering the global importation process, and alternatives in the national market. The detailed modeling implies that the purchase orders that should issue the organization are the result of negotiation and purchasing of multiple offers, mainly for imported raw materials. The model considers in detail Incoterms for trading between regions, and the consolidations of containers in exportation ports. Result: a global sourcing optimization model. Two versions of the models were delivered, GAMS and C linked to Plex and Gurobi solvers. Refined petroleum production and energy services planning model. Challenge: to develop an integrated production and industrial services optimization considering that the optimal management of power of industrial systems implies a holistic position oriented to integrate the production planning of goods with industrial, energy, services that are consumed in the production plant, and finally integrate it with possibilities of self-production and negotiation of this energy in the energy markets. Solution: design and implementation of an optimization model that simulate the production process, and simulate industrial services process, like boilers, pumps, turbines, electricity plants, collector, compressors, etc. The approach considers that industrial processes have variable speed, and that the power consumption as a function of the speed is nonlinear, it is exponential. Service plant, place where various industrial operations, related to the auxiliary services demanded by process plants are developed. Auxiliary service, essential services for the operation of any production system, they allow to guarantee the quality and the continuity of the process, and service unit, facilities that make up the service plant, its function transform the different services to adapt them to the requirements of demand for auxiliary services of the process plant. The main objective is to optimize the management of service plants by considering the fluctuation of demand over time. The optimization of the two plants is carried out in an integrated model. Result: a prototype model that optimizes the oil refining process including industrial services plants at tactical level. A similar model implemented for the Petrobras Recap refinery, São Paulo, Brazil, achieved up to 10% cost reduction. It is part of the oil and gas artificial hypothalamus project, cement plant advanced planning and scheduling. Challenge: to optimize the energy consumption process in cement factories. Solution: design and implementation of a mathematical optimization model to support planning and scheduling of the production batches, Considering as main objective function the reductions of production cost and energy consumption, considering emissions constraints. Result: the model is integrated by three nonlinear submodels. Raw materials blending, kiln, and cement mill. Research and development project. Challenge: to implement an optimization model that integrate the production with the financial modeling to permit the enterprises to implement optimization models for the integrated business planning (IBP) process to improve the decision-making process. Solution: design and implementation of an optimization model that connect financial (ALM) with supply chain planning (SANDOP) models allowing to optimize cash flow and treasury management, working capital, fiscal management, dividends, capital repatriation, payment/prepayment of liabilities, capital and equity structure, and transfer prices. Based on stochastic programming framework, SANDOP ALM may include corporate financial risk analysis. Result: a prototype SANDOP/ALM model was developed by a high professional, as part of his postgraduate thesis in UPC, Universitat Politècnica Catalunya. Additional to the production/distribution variables, it produces financial statements, I, losses and gains, 2, cash flow, and 3, balance of assets and liabilities. The model was applied to optimize transfer prices in a realistic beer global supply chain. Project: advanced planning and scheduling for a small and medium enterprise. Challenge: to implement production optimization mathematical models for SME, small and medium enterprise, PYME in Spanish. Solution: design and implementation 2 optimization models, simulate the plastic production process for strategic analysis, and schedule the daily operations to satisfy the orders of its clients. Result: implementation of the models in a web server to be used as OAS, optimization as a service. Like Herbert Simon, Hypothalamus Artificial Intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.